like to begin talking about methods of integration. We want to be able to find antiderivatives of functions, say f of x, of a wider variety than the type that we know right now. From an application point of view, what this means to us is that we would be able to, say, find centers of masses for regions that are more complicated than the ones that we know about already. We know how to do some integrals. For example, the integral of x squared with respect to x is an easy problem because the function is a constant power of x. We have the rule that says increase the power on the x by 1 and then have the reciprocal of the new power. So obviously 2 plus 1 is 3. My antiderivative would be 1/3 x cubed. And then once you have one antiderivative, add a constant to get all of them. The integral of x to the negative 1/2 with respect to x, which is to say the integral of 1 over square root x dx, increase negative 1/2 by 1, and you get 1/2. I'll have 1 over 1/2 times x to the 1/2 power plus a constant. That is to say 2 times square root of x plus a constant. So that's easy to do as well. You can do this with any constant power of x except for the power of negative 1. We had to go off and do the logarithm trick for that. An antiderivative for the 1 over function is the natural log absolute function. If the power, the exponent, isn't a constant, we don't know how to do that yet. Other things we know about integrals is the integral of a constant times a function is the constant times an antiderivative of the function. Sums and differences act the way derivatives act. The antiderivative of f plus g is just antiderivative of f plus antiderivative of g. Likewise, comment for f minus g. Notice there is no simple thing for the integral of f of x times g of x, or f of x divided by g of x, though. But anyway, these facts that we know so far will allow us to integrate any polynomial. Putting in the full details, I want to find an antiderivative for 7x squared plus 5x plus 2. This is the same as finding an antiderivative of 7x squared, one for 5x and one for 2, and adding them together. Of course, the 7 and the 5 are constant factors, so I can pull them out of their respective integrals. I'll just leave the 2 where it is because it's not of a great concern to me. Antiderivative for x squared, one of them is 1/3 x cubed. Multiply that by the 7, and you'll get this first term, the 7/3 x cubed. Likewise, an antiderivative for x to the first power is x squared over 2. Not forgetting about the 5, you'll have 5/2 x squared. An antiderivative for 2 is 2x. You can check that by taking the derivative of 2x and making sure you get 2 back like you're supposed to. This is one antiderivative. Then I get all the rest of them by adding a constant. Some problems can be twisted around easily into a form that you can deal with. For example, integral of x squared plus 1 over x. Because of the way we add fractions together, that's just the integral of x squared over x plus 1 over x. Of course, x squared over x is x. So if I can figure out the antiderivatives of x plus 1 over x, I'm done. This is x to the first power, so an antiderivative is 1/2 x squared plus an antiderivative for 1 over x is natural log absolute value of x, and then add a constant in. Sometimes you have to do other forms of trickery. If I want to find the integral of 2x plus 3 over 1 plus x squared, if you look at that, the derivative of the bottom, the derivative of 1 plus x squared is 2x, and I have a factor of 2x upstairs. It's too bad that that 3 is in the way. So we'll split this up into two simpler integrals, hopefully simpler. In the first one, the integral of 2x over 1 plus x squared with respect to x, I'm going to let u be 1 plus x squared. The derivative of u with respect to x is 2x. These things are not really fractions, but as you'll remember from Calculus 1, in certain circumstances, we can get away with pretending that they are. This is one of those circumstances. Du is 2x dx. In my integral, I can think of grouping the 2x with the dx. 1 over 1 plus x squared is 1 over u. 2x dx is du. So that turns this first integral into the integral of 1 over u with respect to u, which is on our list. That would be natural log absolute value of u. And since u is 1 plus x squared, I can write 1 plus x squared in instead of the u. The second part was the part that still had the 3 in it. I need to find an antiderivative for 3 over 1 plus x squared dx. 3 is a constant factor, so I can pull it out in front of the integral. And 1 over 1 plus x squared is on our list of things that we know about. The antiderivative for 3 over 1 plus x squared is just 3 times the inverse tangent of x. So altogether, I'll take my natural log of 1 plus x squared, I'll add in 3 times arctan x, and then I'll add the constant of integration in. In section 8.1, there is a table of integrals that we're already supposed to know about. Now, I'm not allowed to show that in this video because of copyright reasons, so if you have the textbook, look in section 8.1 and you'll see a long list of integration facts that we're supposed to already be familiar with from Calculus 1. One of them, number 18 on the list, is written as integral of du over radical a squared minus u squared is arcsine of u over a plus a constant. When they write this, what they really mean is the integral of 1 over radical a squared minus u squared integrated with respect to u, but because we pretend these things are fractions and things are getting multiplied together, if you follow that convention, then this obviously means this. It looks a little strange though. Why write it that way? It's to help you enhance your pattern recognition. If I want to look at the integral of 1 over square root of 9 minus 4x squared with respect to x, this integral has a radical in it, and within that radical, there's a constant squared. I have a constant here, so I could think of the a as being 3. U squared, 4 times x squared is what you get when you square 2 times x. So if I think of a as being 3 and u as being 2x, the square root factor is as it is in this formula. Now, of course, the derivative of u with respect to x would be the constant 2. We pretend that these things are multiplication and fractions. So derivative of u with respect to x being 2 means du is 2 times dx, or that dx is 1/2 times du. One of the most common mistakes I see people make with integrals is they stop writing this differential part down, thinking that it's not important. If you do that, you'll be off by a factor, in this case, a factor of 2. So be sure to write the differential part in. I have 1 over this radical. I have dx, which I'm going to write as 1/2 times du. So my integral literally turns into the integral of 1 over square root of a squared minus u squared with respect to u, except I have this extra factor of 1/2. The 1/2 doesn't bother me in the least. It's a constant factor, so I can pull it out in front of the integral. So this says I'm going to have 1/2 times integral 1 over radical a squared minus u squared with respect to u. That's on the list. This is number 18. This integral is the arcsine of u over a, and then I have to remember my 1/2. Later I'll add a constant to get all of these. The antiderivative that I'm looking for is 1/2 times arcsine of u over a. U was 2x and a was 3, so this is going to be my answer. This seems a little crazy, so I'm going to check my answer. I'll leave the constant of integration out because its derivative is 0 anyway. I'm going to look at the derivative with respect to x of 1/2 arcsine 2x over 3. I can pull the 1/2 out front. The derivative of the arcsine function is the 1 over square root 1 minus squaring function. And I have to evaluate that at the place I was evaluating the arcsine at, namely 2x over 3. And then because of the chain rule, I have to multiply by the derivative of that 2x minus 2x over 3, that is. This derivative is a constant. It's 2/3. So I wrote it over here next to the other constant. The 2's cancel out. I'll have 1/3, 1 over radical 1 minus 4x squared over 9, which at first glance doesn't appear to be right because it doesn't look exactly like the thing I was integrating, but we'll see about that. I can write the factor of 1/3 out front as 1 over square root of 9, because principal square root of 9 is 3. Then if you use properties of square roots to combine this into 1 square root, and then use the distributive law, 9 times 1 is 9. 9 times 4x squared over 9 is 4x squared. We see that the derivative of our alleged answer is the thing that we were integrating. So this is right. This is correct. I want to think about the integral of 1 over 1 plus e to the x. This is not on our list of things that we know about, and I want to mention a common mistake that people will make. The integral of a fraction is not the fraction of the integrals. This integral is not the integral of 1 divided by the integral of 1 plus e to the x, both with respect to x. That would be x over x plus e to the x, and that's not right, as we'll see on the next page. The derivative of a fraction is not the fraction of the derivatives. If you thought that and you checked your answer, you would think that your answer checked, but it doesn't. What we have to do is the quotient rule. So we're going to take our alleged answer, which, by the way, again, is not right, and we're going to calculate its derivative. It's bottom times derivative of the top minus the top times the derivative of the bottom, all divided by the square of what used to be on the bottom. So do the indicated derivatives. Do the algebra and simplify, and you find out that the derivative of your alleged answer is this messy thing, and that certainly is not 1 over 1 plus e to the x, because 1 over 1 plus e to the x is always positive, since e to the x is. But if x were bigger than 1, this number would be negative. There's no way these things can be the same thing. So what are we supposed to do? We have to do trickery, that's what. The 1 in the numerator, you could write that as 1 plus e to the x minus e to the x. This is the old add and subtract trick. Why would we want to do that? Because of the way fractions work, this is going to be this number, 1 plus e to the x over the denominator, minus this number, e to the x over the denominator. And two things happen here. Firstly, when you take something and divide it by itself, you get 1, which is good because I know how to integrate a constant. And secondly, this piece, the piece that remains now, on the bottom, you have 1 plus e to the x. The derivative of that would be e to the x, and a factor of e to the x shows up in the top. So this is going to work out for us. An antiderivative for the constant function 1 is x. The rest of it, let u equal 1 plus e to the x here. The derivative of u with respect to x is e to the x. Du is e to the x dx. And I have a factor of e to the x dx in the integral. E to the x dx is du, so I'll write that part there. The only thing I haven't accounted for is the rest of the fraction. 1 over 1 plus e to the x is 1 over u. That turns my integral into integral 1 over u du, which is on the list of things that we know how to do. That's going to be the natural log of absolute value of u, natural log absolute value 1 plus e to the x. It might be worth mentioning 1 plus e to the x is always positive, so I could turn those absolute value symbols into parentheses if I wanted to, but I'm just going to leave it as is. Putting the pieces together, the integral of 1 over 1 plus e to the x is x minus natural log, absolute value, 1 plus e to the x, plus a constant. If you check this in the same way that we did before, making use of the fact that the derivative of natural log absolute value is the 1 over function, and doing a little bit of algebra, you end up with 1 over 1 plus e to the x, and that is the thing that you were integrating, which convinces me that my answer is right. As you can imagine, the number of variations on a theme, the amount of trickery that you might need to do is practically unlimited. If I have the integral of 1 over square root of 6 minus x squared minus 2x with respect to x, that doesn't seem to be anything that we know about. But if you group the parts that have x in them together, and then look at the x squared plus 2x, you think to yourself, it's too bad it doesn't say x squared plus 2x plus 1, because that would be a perfect square, and I could do something with that. So as usual, add in the thing that you wished was there, and then subtract it right back off. Your integral is the integral 1 over radical 6 minus the quantity, the square of x plus 1 minus 1 with respect to x. I'm going to have 6 minus 1. I'm going to have a 7 as a constant, and I'll be subtracting away the square of something. So we're going to integrate 1 over the square root of 7 minus x plus 1 quantity squared. This looks like one of our forms that we know about again. I'm going to want the a squared to be 7, so I'll take the a to be square root of 7 here. The u, the thing that I'm squaring and subtracting away from a squared, is going to be x plus 1. For this problem, derivative of u with respect to x is 1. So du is 1 times dx. So du and dx for this particular problem are the same thing. This is the integral I have to do. Our list says that this is arc sine of u over a plus a constant. U is x plus 1. A is radical 7. So my answer is going to be the arc sine of x plus 1 over square root of 7 plus a constant. As you can imagine, there is an almost limitless variety of integrals that could involve clever trickery to turn it into something that we can do something with. At the very least, be sure to look at the beginning of section 8.1 and make sure you at least know that there are formulas for various types of integrals. On another level, no matter how clever you are, it may be that those tricks that we already know about won't be of any help to you. For example, if I wanted to find an antiderivative of x squared e to the x, or x squared minus 5x plus 1 multiplied by cosine x, we don't have any way at all of doing that right now. So in the next section, we're going to begin talking about new methods, and the first one will be integration by parts. Once we know integration by parts, these kind of integrals will be easy for us. That's all I wanted to talk about in this first video on methods of integration. I hope everyone's having a good day. I'll talk to you again soon.